Okay, and so we've been talking about hydrogen atom stationary states. And we'd worked out a lot of information about these stationary states in the last lecture, including the expectation value of the radial coordinate of the electron in an arbitrary state. And just to review, what we'd found was this. In a state specified by NLM, N is the principal quantum number, and the other two are angular momentum quantum numbers. Okay, this turned out to be the Bohr radius, A0, divided by 2 times the quantity 3n squared minus L times L plus 1. Okay, and A0, the Bohr radius, reminder, that was equal to h bar squared over the mass times the charge on the electron squared, which turns out to be about 5.29 times 10 to the minus 11 meters. Okay, and so today we're going to start with a different topic, which is, instead of the expectation value of just r, what about the expectation value of r to the n? And that's going to turn out to be useful and important for things we'll do a little bit later. So we're going to just do them in the ground state, and then you'll get to actually do, for the first excited state, you'll get to do that for homework. So the question we're asking is, in the ground state, what is the expectation value of the operator r to the nth power? And I'm using capital N rather than little n because little n is reserved for the principal quantum number. Okay, so to do this, we just set it up. So we're asking for this expectation value. And so we're going to work in position space, which means we do an integral over r, remembering the factor of r squared that comes from spherical coordinates. And we do an integral over phi from 0 to 2 pi. And we do an integral over cos theta. I think I've mentioned this before, but this is often called just integral d omega. Okay, and then in position space, the operator r to the n is the number r to the n. And then we are putting in the wave function squared, which is 1 over pi Bohr radius cubed times e to the minus 2r over Bohr radius. So this right here, that factor is the wave function for the ground state as a function of position squared. So in the ground state, we're lucky because nothing depends on the angles, theta and phi, and so this integral is just turning into 4 pi. Okay, and so we can rewrite this as 4 over the Bohr radius cubed times this integral, 0 to infinity, r to the n plus 2 power. The 2 comes from here, combined with the r to the n we're actually calculating. And then there's e to the minus 2r over Bohr radius, dr. Okay, and so we can rewrite this by making a change of variables. U is going to equal 2r over the Bohr radius. du is 2 over the Bohr radius dr. And so this turns into 4 over Bohr radius cubed And then there's a factor from the change of variables of Bohr radius over 2 to the n plus 3. There's n plus 2 from the dr, and then there's this part that gives the other factor. And then what's left is a dimensionless integral, 0 to infinity, u to the n plus 2, e to the minus u du. Dimensionless integrals are good because this one is just something one can easily look up. And the answer here is this is equal to n plus 2 factorial. It's just a definite integral. Except it turns out it's n plus 2 factorial only if n is large enough for n greater than or equal to minus 2. Because if n is less than that, then it's actually going to diverge at the lower limit of integration at 0, because then you're taking this to a power that's going to blow up at u equals 0. We never have to worry about the upper limit of integration because the exponential is always going to kill the function and make the integrand be well behaved at large u. So the upper limit of integration isn't a problem. But for the lower limit of integration, this is actually infinity for n less than minus 2. Okay, and then this part we can simplify to Bohr radius to the nth over 2 to the n plus 1. And so the whole thing works out to be n plus 2 factorial divided by 2 to the n plus 1 times the Bohr radius to the nth power. So if we think about it, we could have sort of guessed the general form of this just by dimensional analysis. There's really just one scale in the problem, and that's the Bohr radius. And so if we're taking the expectation value of r to the n, it had to be proportional to the Bohr radius to the nth power. And then in front of it, there's some dimensionless stuff. And it just so happens that it turns out to be n plus 2 factorial over 2 to the n plus 1. Okay, so we've done this in general. And now we can look at some specific cases, including some checks. So one thing we can do is plug in n equals 0. And then we're computing the expectation value of 1. According to our formula here, that's 2 factorial over 2 times the Bohr radius to the 0th power, which is all equal to just 1. And that's a check because really what we're doing there is just calculating the norm of the state. And the norm of the state was designed to be 1. Okay, we can also do, so this was n equals 0. We can also do the expectation value of r to the first power, which according to our formula is 3 factorial divided by 2 to the 2 times the Bohr radius to the first power. And so that's 3/2 times the Bohr radius. So one perhaps might have naively guessed that the expectation value of the radial coordinate would be equal to the Bohr radius, but no, it's equal to 3/2 times that. And we actually already knew that because that comes from here. So if we plugged in n equals 0 and, n equals 1 and L equals 0 in that formula, it would have been 3/2 times the Bohr radius. Okay, so that's another good check. That was for n equals 1. And now we can plug in different other values of n. Here's one we're going to need later today, in fact, very soon. And that's what if n is minus 1? We're computing the expectation value of 1 over the radial coordinate. So our formula says that's 1 factorial over 2 to the 0 times 1 over the Bohr radius, which is just 1 over the Bohr radius. Okay, and then we can do 1 over r squared, and that turns out to be 2 over the Bohr radius squared, and 1 over the radius cubed. The expectation value turns out to be So that's where this comes in. If n is too small, then the expectation value is not defined. So this is going to be infinity. And similarly for example, the expectation value of 1 over r to the 4th power. And any larger negative power of r. So those are negative powers. We can also do positive powers. So if we take the expectation value of r squared, that's, according to our formula, 4 factorial over 2 cubed times the Bohr radius squared, or 3 times the Bohr radius squared. And then similarly, the expectation value of r cubed is 15/4. And the expectation value of r to the 4th is 45/4 Bohr radius to the 4th, etc. So now one thing we can do is we can calculate what is the uncertainty in the radial coordinate. So for that, we go back to our general formula for uncertainties, which looks like that. Okay, and then plugging in the results we found, that's the square root of 3 Bohr radius squared minus the square of 3/2 the Bohr radius, all squared. And so that turns out to be the Bohr radius times the square root of 3 minus 9/4, which is square root of 3 over 2 times the Bohr radius. Okay, so those are all pieces of information about how the radial coordinate expectation values behave for the ground state. We can also ask what happens to the momentum expectation values. So the first thing to note there is, let's say we're just going to calculate the expectation value of the momentum operator itself, which is a vector. And the thing is, because it's a vector, it has to be 0 by symmetry. And so the reason for that is, if it's a vector, it has to point in some direction. But for the ground state of hydrogen, that's spherically symmetric. There's no particular special direction that it could possibly point in. And so it's forced to vanish. So that argument won't work. I should say no special direction in ground state. That argument won't work for the excited states of hydrogen, because let's say I'm taking a state that has non-zero angular momentum with respect to the z-axis, then there is a special direction, and that would be the z direction. And so from that argument wouldn't tell you that the expectation value of p is 0 necessarily. So there you'd have to compute it. But here we're just talking about the ground state. So then you could ask, what about the expectation value of the momentum squared? Another thing we'll use a little bit later today, but it's just useful in general. So it turns out there's an easy way and a hard way to calculate this. We will start with the hard way because it builds character, and then we'll come back and say what would have been the easier way. The other thing about the hard way is it's sort of straightforward to see how it works. So the expectation value of p squared is, we just work in position space. And so just like we did for the expectation value of position, we set up our integral. Okay, so we're integrating over all of our spherical coordinates. And then we're going to put in the wave function, psi100 for the ground state, complex conjugated, times the operator for momentum squared in position space, which is minus h bar squared Laplacian, and then multiplied by psi100 again. Okay, so this factor here is 1 over the square root of pi Bohr radius cubed, e to the minus r over Bohr radius. That's just plugging that in. We also plug it in here. And so then if we take the Laplacian of that, that's minus h bar squared times 1 over r squared partial with respect to r of r squared partial with respect to r, acting on our psi 100, which we write in here again. Okay, so it's that, plus there's some theta and phi terms. And those vanish, though, because they all involve derivatives with respect to angular coordinates. And our wave function here doesn't have any dependence on angular coordinates. Or another way of saying it is that because we're in the L equals 0 state, this is proportional, the angular part is proportional to the angular momentum. And so this vanishes. One way of saying it is it's due to being in the L equals 0 state. So in any case, they're not there. And so now we just need to evaluate this mess. Once again, this part is, fortunately, because there's no theta or phi dependence anywhere, this part is just 4 pi. And so we can, first of all, pull out all the constants that we can pull out. And so there's a 4 over Bohr radius cubed. There's a minus h bar squared from this, or from there. So let's pull that out. And then finally, we have the radial integral, 0 to infinity dr. Now, this r squared nicely cancels with this 1 over r squared, so at least we don't have to do that. And then there's this exponential that we should put in here. So there's e to the minus r over Bohr radius. And then there's derivative times r squared d by dr, e to the minus r over Bohr radius. Okay, so now we just have to compute these derivatives. This derivative right here is just going to give minus 1 over a0, e to the minus r over Bohr radius. And then when we take the derivative of that multiplied by r squared, it's minus 1 over a0 times 2r e to the minus r over a0 minus r squared over a0 e to the minus r over a0. Okay, and then when we do the integral, then we have to multiply by the other factor here of e to the minus r over a0. So the whole thing looks like this. Integral 0 to infinity dr. Now there are two factors of the exponential. And then there's minus 2r over a0 plus r squared over a0 squared. Okay, and both of those factors make nice integrals that one can just look up. And so the answer here turns out to be negative Bohr radius over 4. And now, fortunately, this minus sign cancels with that minus sign right there. And the 4 cancels with that 4. And so the whole thing for the expectation value of p squared in the ground state of atomic hydrogen is h bar squared over a0 squared. So up to the numerical factor in front of that, we could have guessed this, because if you're trying to make something that has units of momentum, and what you've got to play with is h bar and the Bohr radius, then pretty much this is the only combination that you can make. So what the number is in front, of course, is harder to guess. There you sort of have to do the integral or something else similar to it. But it sort of had to be of that form. So now we can check this, and when I say check this, this check is actually an alternative method that we could have used to do the computation, which, as you'll see, would have made things a little bit simpler. So the check is to think about the expectation value of the Hamiltonian in the ground state. So that's easy because we know what the energy of the ground state is already, so we know its expectation value. But just as an operator, that's equal to the expectation value of the momentum squared over twice the mass. We've just worked out what the expectation value of p squared is, minus e squared times the expectation value of 1 over r. And we also worked that out earlier today. Okay, so in particular, what we found was, if I just take the previous result and I divide by twice the mass, that's equal to h bar squared over twice the mass times the Bohr radius squared. And then if you plug in what's the Bohr radius, it looks like this. And then we can write this in the form mu times e to the fourth over 2h bar squared. Okay, and then on the other hand, minus e squared, expectation value of 1 over r, from what we found, is minus e squared over the Bohr radius. And again, we can write that in the same form as the previous expression. Okay, and so that's minus the same thing, but with no 2 in the denominator. And so when we add those together, the total is minus mu, the mass, times e to the fourth over 2h bar squared, which is otherwise known as negative 1 Rydberg. Okay, which is minus 13.6 electron volts, which is indeed the expectation value of the Hamiltonian. So if you turn it around, you could have said, if we knew that, we did know that to start with. And so if you don't like taking derivatives, like this mess that we had to do here, we could have gotten this by instead using what we knew here and moving that to the other side of the equation. And then we would have been able to solve for p squared over 2 mu without having to do any derivatives or then integrate the previous result. Okay, so that would have been a shortcut. And then let me remind you, this was all for the ground state. And so for homework, you're going to get to look at the n equals 2 state. This was the n equals 1 state. Okay, any questions on that? All right, so in this business, dimensional analysis is a big help. And so let's think more about that. So dimensional analysis really could have told us what the Bohr radius would have been up to a factor that might have been 1 or 2 or something like that, just by thinking about what should be in quantum mechanics the size, it's sort of a fuzzy concept, so I'm putting it in quotes, of the atom. Okay, so that's the Bohr radius, and what we found was it was h bar squared over the mass times e squared. And so what I want to mention is that we could have guessed this from the following considerations. That first of all, the size of the atom only has a finite size because it didn't collapse. And as we showed on the first day of class, it would have collapsed in classical mechanics. The atom would have just shrunk to 0 size. And so if h bar goes to 0, which is the classical limit, then this thing should go to 0. So that's telling us it should depend on a positive power of h bar. The other thing is that, let's say E was very large, then also it should go to 0. So that's because if the E is very large, then the electron is extremely tightly bound and it can't go wandering off. And so the size of the atom should have gone to 0 in that limit too. And similarly, it should go to 0 if the mass of the electron is very large, for really the same reason. If the mass of the electron is very large, then it's super heavy and sluggish, and it can't really escape from the nucleus very easily. And so again, it would shrink to 0 size. So these last two facts are just telling you that the mass and E should go on the denominator, right? And so if you know h bar goes in the numerator, and you know mass and E go in the denominator, and you try to find something that has units of length, then pretty much that's all there is. Well, I say pretty much because it's not quite true, because there's another dimensionless quantity you can make, and that's called the fine structure constant. So a dimensionless quantity. And it's usually traditionally written as alpha. It's defined to be E squared over h bar times the speed of light. If you put in the units, that turns out to be dimensionless. And its numerical value is 1 over 137.036, something, something, something. So there was, at one point in time, there were people who tried to explain why it should be exactly 1 over 137 with some dubious math. And it turns out that was all baloney, because they found out later it wasn't exactly 1 over 137. Here, c is the speed of light in vacuum. Okay, and so there's no particular reason it has that value, it just does. But once you've got a dimensionless quantity, you can take any other dimensionful quantity and multiply it by powers of that. And so there's another length scale that you could make, which is you take the Bohr radius and you multiply by some powers of the fine structure constant. So the most obvious thing to do is to make another length scale characteristic of this problem of the hydrogen atom by taking the fine structure constant times the Bohr radius. That's still a length, and it's given a name, which is the reduced Compton wavelength of the electron. So the symbol for it is lambda, which is usually used for wavelengths, with a little slash through it, with an E for electron, and the name is reduced Compton wavelength of the electron. The reason it's called reduced is because there's another Compton wavelength of the electron, which is just 2 pi times this. Dimensional analysis doesn't tell you where to put factors of 2 or pi, and so you could have defined it that way. But in any case, this one is h bar over the mass times the speed of light. Okay, and that's about 3.86 times 10 to the minus 13 meters. So it's a very small length scale, much smaller than the Bohr radius, because alpha here is much less than 1. So the interpretation of this length scale is it can't be the size of the hydrogen atom, it's much smaller. And so what it really is this is the distance scale at which everything that we've done is wrong. It's the distance scale at which electron-positron pairs are important. And notice that we have not talked at all about positrons when we talked about the hydrogen atom, yet positrons do exist. And so to the extent we haven't taken them into account, we've been making a mistake. So this is at which this becomes important. Okay, and so to understand that, to understand why this is very roughly true, and we're just doing very hand-wavy order of magnitude estimates here. Suppose we confine an electron to a size of comparable to the reduced Compton wavelength. So suppose we confine electron to the size delta x. We're going to set delta x equals to reduced Compton wavelength in a minute. Okay, then delta p, the uncertainty in the momentum, should be about h bar over delta x from the uncertainty principle. And for a relativistic particle, the uncertainty in the energy should be the speed of light times delta p, because energy is just the speed of light times momentum for a relativistic particle. Okay, and our electron will be relativistic because it's going to have a large energy. And so now if we put in for that delta x, if we say it's much less than the reduced Compton wavelength, which is h bar over the mass times the speed of light, then we find out that the energy uncertainty is much, much larger than twice the mass times c squared. So I'm putting in the factor of 2 here just to illustrate that this is the energy needed to make an electron-positron pair, because the energy needed to make an electron is the mass times the speed of light squared. Positron is the same. Of course, you can't just make an electron because it wouldn't conserve charge, but you can make an electron-positron pair because they have opposite charges. Okay, and so if you try to make something, if you try to look at length scales that are very small compared to the Compton wavelength, you should be making lots of electron-positron pairs, and then the analysis we've done up till now will be wrong. Okay, so just to say that in words, so if we tried to localize the particle, in this case the electron, to a position smaller than its Compton wavelength, then pair production, in this case electron-positron, is important. So the question is, why was it that we could get away with ignoring that? And then we can look at we can compare this energy scale associated with this with 1 Rydberg. So 1 Rydberg is equal to, one way of writing it is the mass e to the 4th divided by 2 h bar squared, which is the mass times c squared. I'm just rewriting it. Okay, and so I've rewritten it in that combination, but that combination is equal to the rest mass, the rest energy of the electron, which is 0.511 MeV, times 1/2 times the fine structure constant. So this is the rest energy for an electron if it weren't in a hydrogen atom. And so the whole point is that just that the actual energy of a hydrogen atom is much, much smaller than that because of the factor of the fine structure constant squared, which is 1 over 137 squared. And so because this energy is much, much less, we don't have the opportunity to, at least it's not super important that we worry about making these electron-positron pairs. So it turns out, and we're going to go over this in a minute, and if you take Physics 661 in much more detail, it does make a little bit of a difference. And so if you're going to do very careful measurements, you do have to take this into account, but it's not a huge effect. Okay, so in fact, let's see how that goes by asking the question, how big are relativistic effects for the hydrogen atom? And we're specifically asking about the energy. We could ask about other things like the size of the hydrogen atom, but if we understand how it affects the energy, that will give us a good indication of what the relativistic effects are. Okay, so recall that the Hamiltonian, the kinetic part from non-relativistic effects, is the momentum squared over twice the mass. And now let's try to write down a relativistic version of this. And I should perhaps emphasize that what I'm about to do is actually only part of the story. It's not the complete story. But naively, we could proceed by just writing down the classical special relativistic energy, which it happens is, according to Einstein, c squared times p squared plus the mass squared times c to the fourth. And then I can subtract off the rest mass of the electron, or the rest energy of the electron, which looks like this. Okay, oops, I made a mistake there. That should be just 1 power of mu. Oops. Okay, and then the way we can deal with this is we can take the square root and factor out this factor of mu c squared, and then what's left is 1 plus p squared over mu squared c squared minus mu c squared. And then we can expand the square root using the binomial expansion. So that's 1 plus p squared over mu squared c squared with a factor of 2 in the denominator. And the next term turns out to be p squared squared over 8 mu to the fourth c to the fourth. And this continues on, minus mu c squared. So what I've used there is the binomial expansion. Which says if you take a square root of 1 plus a small number, that's 1 plus 1/2 x minus x squared over 8 plus dot, dot, dot. And so we've just applied that with x being p squared over mu squared c squared, which we're taking to be a small number because if you plug in the expectation value of p squared, you find out it was indeed a small number. Okay, and so from that, let's see what happens. H relativistic is, so this factor right here just cancels against that one. And so we're left with this factor multiplied by the prefactor, which is just this. And so the leftover part, so let me just write that. So that's p squared over 2 mu. And then the next term is minus p squared squared over 8 mu cubed c squared. And then there's going to be another term and more terms that are even smaller than that. So this part right here, we could estimate as the change in the energy due to including relativity. Okay, and so it's negative. And we can estimate its magnitude. We're just going for an order of magnitude estimate. So we're not going to worry too much about factors of 2. Okay, but delta E, relativity, is, so what we're going to do for this estimate is just replace p squared by its expectation value. Okay, and earlier in the lecture, we worked out what that was. It was h Bohr squared over Bohr radius squared, and we're squaring it. Now, technically, that's not quite right because the expectation value of p squared squared is not the same thing as the expectation value of p squared, then squared. But we're just going for an order of magnitude, so we're not worrying about things like that. And that's divided by 8 times the mass cubed over c squared. And so now we can rearrange this. We can write it as minus h bar to the 4th times mu e squared over h bar squared. I'm putting in the Bohr radius there. That's to the 4th power over 8 mu cubed c squared. I'm not sure why I'm keeping track of the 8 because it's not really rigorous here. But then you can write this as minus the mass e to the 8th power over 8 h bar 4th c squared. There's lots of different ways to write this. I'm aiming, though, to get this in form of the rest energy squared of the electron, which is minus mu c squared times 1/8 times e to the 8 over h bar to the 4th c to the 4th. And the reason for writing it that way is that's the fine structure constant to the 4th power. Okay, so this is all rest energy of the electron times a factor of 1/8 that we really shouldn't perhaps have kept track of, times the fine structure constant to the 4th power. So that's a really small number. And the 1/8, as I keep mentioning, is not something we should take too seriously. It turns out when you do a correct analysis, which is not so easy, then the minus 1/8, it turns out, turns into a factor of 1 over 2n for states with principal quantum number n. And that's true if L is not zero. Or sorry, if L is 0. In other words, if it has 0 angular momentum. And then the same thing turns out to be 0 for states with L not equal to 0. So it just so happens that for non-zero angular momentum, you don't get this correction. And so putting it together, when you do this correctly, the change in the energy coming from relativity, at least the powers of fine structure constant were correct. And so this goes like fine structure constant squared times the energy of the state divided by n. Okay, and this is known as fine structure because it's small. And we'll learn how to do this correctly without just the dimensional analysis hand waving in Physics 661. Okay, but so the moral of the story is when you add these corrections, the relativity corrections, you get an extra factor of alpha squared. And that's a small number. And so that's why we can get away with not worrying about it too much. Okay. So the whole, in other words, the whole reason single particle quantum mechanics, where we neglect positrons, the only reason it works is because of the accidental fact that the fine structure constant is much, much less than 1. You could imagine we lived in a world where the fine structure constant was 3, and then everything we would have done talking about the hydrogen atom would have been completely wrong. But that's not the world we live in. Okay, another thing you can talk about is you can talk about what's the velocity of the electron in the hydrogen atom. Okay, and I'm putting velocity in quotes, and one reason for that is you could define it to be the expectation value of the momentum squared, square rooted, to give an actual number that's momentum, divided by the mass. And so that's very roughly h bar over the Bohr radius divided by the mass, which you can rewrite as h bar mu e squared over h bar squared divided by the mass. And so that's e squared over h bar, which is the fine structure constant times the speed of light. So what have we learned there? We've learned that in units of the speed of light, the velocity of an electron, so usually we write beta for the ratio of a velocity to the speed of light, that's about 1 over 137. Okay, so electrons, if you want to think semi-classically, electrons in the hydrogen atom are moving much less than the speed of light, but not that much less than the speed of light. They're within 1% of the speed of light. All right. Another thing we can do with the stuff we've learned about the hydrogen atom is we can look at the spectrum of light that's emitted and absorbed by atomic hydrogen. It's very important that we specify atomic hydrogen here because on Earth, most hydrogen is actually molecular hydrogen, where it's H2. But in outer space, there's lots of atomic hydrogen. And so if we have a state with principal quantum number n, and another one that's lower with principal quantum number n prime, and we transition between those states, we can do that by emitting a photon. And the photon will be the difference in the energies of those two states, will be its energy, which will be the h bar times the angular frequency, as Einstein told us, for this transition, which is the energy n minus the energy n prime. And so from that, we learn the angular frequency of the light emitted is going to be 1 Rydberg, 13.6 electron volts, divided by h bar, times the factor that comes from the n's, which is minus 1 over n squared, plus 1 over n prime squared. So now one can just plug in different n's and n primes to find out what the energies and what the wavelengths and angular frequencies of the light will be. So I'll just do one today and we'll do the others next time. The most significant one is the Lyman series. And the Lyman series is just all the light that you get from transitions to the ground state. So it would make sense that those would be the most important ones. You've got an atomic hydrogen state minding its own business, and then it gets excited by something, maybe it bumps into something, and then it decays back to the ground state where n prime is 1. And so the angular frequencies for that are 13.6 electron volts over h bar times 1 minus 1 over n squared. And you can do that from any of the states n equals 2 or 3 or 4 up to super excited states with basically infinite n. So now the wavelength is just 2 pi c over that omega. And so if you plug in the numbers, there's the n equals 2 line, where you're going from the n equals 2 state to the n equals 1 state, where the wavelength, when you put in the numbers, is 1.216 times 10 to the minus 7 meters. This is very famous in astronomy. This is known as the Lyman alpha line. And then you can do lambda 2 or lambda 3, 1 up to lambda infinity 1. And when n becomes very large, this factor right here is just getting very small, so it doesn't matter too much what it is. And you start to approach a limit of what the angular frequency and the wavelengths are for very large n, and that turns out to be about 9.118 times 10 to the minus 8 meters in wavelength. That's called the Lyman limit. That's where all these lines sort of coalesce into one line. And all of these are in the ultraviolet, so you can't actually see them with the naked eye. But astronomers can see them because they're clever and they can deal with ultraviolet detectors. Okay, so sorry, it looks like I went over a little bit of time today, but next time we'll talk about the lines that you can see in the visible from the hydrogen atom, which are called the Balmer series. And we'll talk about the other lines and then start talking about what all of this has to do with spin. All right, so that's it for today. Are there any questions on the lecture? Okay, if not, then I'll turn off the recording.